Thank you, Tony. Thank you for organizing this. I'm very happy to be here. I'm just sorry that I won't be able to wreak havoc tomorrow with your, with your nice machines. So the title actually wasn't decided. It was decided by the organizer, and I'm very happy about it. It's like it works perfectly fine. I was a little bit confused about exactly what I should do. It says tutorial, so it's a little bit of a mix of general statements about transport in two-dimensional materials and some of the research we've done in the past few years about this topic. So it's a list of the collaborators that we have. They've been working on this. Postdocs, they've been working with me. Junhua, a wonderful postdoc, then now she moved to Riverside, unfortunately. Dries, a couple of graduate students, actually 3 graduate students, an undergraduate student, and then these are some of the external collaborators that have been working on these topics in the past 5-6 years. Okay, so why do we need to basically think about 2D somehow in a different way? Is that any different than 3D or so on? Yes, the first thing that you notice is that you calculate, for example, the resistance using the standard formula for a hyper cube in dimension d. Then you see that something funny happens in 2 dimensions. Basically, this exponential basically becomes 0, so that the resistance scales exactly as the resistivity. So one consequence of that is that in 2D you might have some more universal behavior that you would expect in 2D. And so that's, for example, something that also stays behind the universality of some of the quantum Hall results. The quantum Hall effect is another big feature of 2D. So basically it turns out that you can only have quantum Hall effect in even dimensions. You can have 2, 4 dimensions. We live in 3 dimensions, so we cannot get to 4, but 2 dimensions is accessible. And so that's all kind of effects. I call them quantum Hall effects. You can have the standard quantum Hall effect based on charge, but then now we know we have quantum spin Hall effect, quantum anomalous Hall effect, and so on. Another feature that happens in low dimensions in 1D and 2D is that the motion of a single charge impurity can change the conductivity by a huge factor. Okay, and so I'll show you a little bit what is the consequence of this, for example, when it comes to the something like 1/f noise. Now, 2D electron system. 2D, it's a very general term. So we have different kind of 2D system. We have the what I call standard 2DEG, standard 2-dimensional electron gases. They've been around for a long time. And so these, basically, you create a 2-dimensional system at the interface of 2 semiconductors. Typically, it's gallium arsenide and aluminum gallium arsenide. The thing to notice is that the thickness of this 2-dimensional system is about tens of nanometer, 10 nanometer. So it's 2D, but it's not exactly 2D as, for example, graphene, in which the thickness is just 1 atom. So 2D graphene is really the ultimate 2-dimensional system. So you can expect that all the 2D effects might be somehow enhanced or more robust in a system like graphene. There is another 2 important differences between a system like these 2 DEGs. One and graphene is that one is the type of the bands. So here you have parabolic bands. In graphene, you have linear bands. The gap typically is larger. And so in graphene, actually, you go to the extreme case in which the gap is 0. And then there is also this very interesting lock-in between the direction of the momentum and the direction of the spin or pseudo-spin. So pseudo-spin if it's graphene, in which you have the sublattice, or spin if you're talking about the surface of a topological insulator. And then another thing that you can do with this new 2-dimensional material is basically you can have a small gap, a gap of only hundreds of millielectron volt that we heard this morning. It's something that might be very interesting for possible low power logic, but it also poses some interesting challenges when it comes to deal with the effects of disorder. And so one system where you can have these small gaps and actually tune these gaps is bilayer graphene, in which by simply applying this, tuning the strength of the perpendicular electric field, you can change the size of this gap. Okay, so I'll talk a little bit more about the graphene and bilayer and ATIs, not so much about this part that basically has been covered has been known for a long time, but it's still very interesting. Now, one of the things I've been working a lot is figure out what is the fate of disorder in these systems. And then what is disorder? Disorder is different depending on the system that you're considering and the regime you're considering. For example, as we already saw this morning, for these standard 2-dimensional electron gases, the limiting factor at room temperature is the scattering of the electrons of the phonons. Okay, so if you see that, no matter what is the quality of your sample, when you go to room temperature, they all fall on the same curve. Basically, this is the mobility as a function of temperature. And so at room temperature, they all fall on this curve. This is basically the phonon-limited mobility. because the scattering, the phonons are there, no matter how clean is your sample. Even if you have very few impurities, they're going to your mobility goes down because of the phonons. On the other hand, graphene, as you also saw this morning, because of the phonon spectrum that it has, at room temperature, basically, it doesn't care about the phonons. The phonons are have a very limited effect. And so as a matter of fact, as a function of temperature, from very low temperature all the way to room temperature, the mobility of graphene is pretty much constant. And at room temperature, it can be much higher than the mobility of even the best two-dimensional electron gas in a semiconductor. So here, for the point of this slide is that if you're talking about 2 days at room temperature, phonons are the dominant source of scattering. If you're talking about graphene, we're talking about quench disorder, so impurities. Okay, and these impurities, I would like to classify them in 2 main different categories: short-range impurities, in which in momentum space the profile of the potential disorder is basically just a constant, or long-range impurities, in which this one is not a constant but depends on Q. And then you have other kind of disorder also in this kind of system like graphene, basically ripples or wrinkles that you can fold back in a special type of long-range disorder. And these are a couple of papers relevant for this kind of regime. It's interesting to look, we did some work for the surface of ATI in which you have an effective 2-dimensional system. In that case, basically, you have both phonons and quench disorder that play an important role. And then which one dominates, it depends on the doping, on the impurity density, and the temperature. So TIs are a little bit more tricky. So typically, if you have this kind of 2 different type of disorder, if you assume that the scattering is independent, the scattering from the phonons and the disorder is independent from each other, then the scattering time, the inverse of the scattering time can be estimated as the sum of the inverse of the scattering times. Okay, so that simplifies a lot the things. So how do you calculate? What we want basically is to calculate typically the conductivity of my 2-dimensional system. How do I do that? Well, the standard, the easiest way is to basically go and do the semi-classical calculation using Boltzmann theory. So this sigma is the conductivity, then d epsilon is the density of states at energy epsilon, v is the velocity of my electrons, a tau transport, this is the relaxation time, and f is the Fermi occupation number. And so this tau transport can be calculated using this integral where w is nothing but the relative probability of having a scatter, basically if you have an electron with momentum p prime to then find an electron with momentum p. And you can write it this way with this factor that basically it's 1 minus the direction of the scattering electron and the direction of the electrons after the scattering. And so this is an important factor that basically it's the way to weight, basically tells you that if you're trying to calculate the conductivity, the kind of scatterings that basically scatter you completely backward are more important than the kind of scattering they just tweak you a little bit forward. And so this basically is what captured by this factor. You can do another way to get to this kind of result is using the so-called linear response theory. So this is the situation in which you calculate the response of your system to a small perturbation. In this case, basically, we want to see what is the effect of the system after a small external electric field. And so the way you can model this, you have a Hamiltonian, that is the Hamiltonian of the system without the electric field, and then you have this perturbation. H here is any generic field, and phi is the field that couples to the field H. And so you can do through the motion and do some algebra. And then if you do that, you find out that basically the response, basically the expectation value of your field phi due to this perturbation field H can be written in this form. So basically, it's an integral over all times of this field H multiplied by this prefactor, where this prefactor is what we call the response function of the variable phi to the external field H, and turns out to be equal to the expectation value of the commutator of phi with itself, evaluated on the ground state of the unperturbed system. So the key point that I would like to, for the students especially, to take home is that the conductivity or any response function in the linear response regime, it's a property of the system. It doesn't have nothing to do with external perturbation. Okay, so because this one, it's evaluate expectation value for over H naught. So this is basically on a classical regime. This is nothing but the fluctuation dissipation theorem that basically tells you that the dissipation of a system is proportional to the amplitude of the fluctuations of the system at the final temperature. And so in this case, you also have quantum mechanics playing a role into the fluctuation. But this is basically very general. And so now if I want to calculate the conductivity, I can basically think of this H as the field that couples to the current. It turns out that that field is the vector field. So this is now the form of this, this is the form of the perturbation. Now, if I remember that typically we would like to relate the current not to the vector field, but to the electric field. And so I remember that E is nothing but the derivative with respect to time of the vector field. And so now I use this, basically the definition of sigma is given by this relation. And so once I go through this algebra, I can find that the conductivity is nothing but chi, basically the expectation value of the current correlator divided by omega. So this is very general, and so I can use it to calculate this chi for any kind of system, for any kind of disorder, any kind of impurity in principle. In practice, of course, it becomes tricky. But this also will become useful where toward the end, if I have time, I can see how this way of expressing the conductivity is related to the quantum Hall effect. Okay, so another way to, this is just a little bit of theory, how to relate this to the diagrammatic way of doing things. So if I have my electron and the scattering of impurities, that basically what it's going to cause is going to cause like a relaxation time. So my momentum eigenstate is not a good eigenstate anymore. It has a final lifetime. That final lifetime is expressed by tau, and 1 over tau is nothing but the imaginary part of the self-energy. That you can calculate, so where this cross is just the strength of the disorder of a single impurity, and assume all the impurities to be the same. The point I'm trying to make here is that the transport time that we saw before in the context of the Boltzmann theory is not the same as this tau. Okay, so and this transport, in order to calculate the transport time, you need to calculate the response function, your chi or sigma, using what I said before. So you need to calculate the current correlator. And in order to calculate that, you have to be careful to also include these kind of diagrams where you have the kind of like synchronous scattering of an electron moving forward and scattering of the same impurity for an electron moving backward. And so this is so-called ladder diagrams. And you have to sum all of the ladder diagrams. By doing that, you're going to find out what is sigma. And then from there, if you want, you can extract what is the transport time. And then the statement is that in general, this transport time is different than the quasi-particle relaxation time. We've been spoiled because basically this is not the case for short-range disorder in a standard two-dimensional electron gas. If you have short-range disorder, as you typically can always approximate most of the disorder in these two-dimensional electron gases in semiconductors as a short-range disorder, then in that case, the transport time coincides with the relaxation time. But in that case also, if the disorder, for example, in your gallium arsenide is not short range, then this is not true anymore. Okay? What is interesting is that for systems like graphene and the surface of a DI, even if you have short range disorder, the transport time and the relaxation time are different. And this has to do with the chirality. So basically, the reason why these two are different, and for graphene, for example, they're different by a factor of 2, is because basically if you have backward scattering, now, because these two states have opposite pseudospin, there is no overlap. And so that backward scattering actually counts less than we would expect. And so as a consequence, the transport time is actually larger than the tau. So this is something to keep in mind when you basically have systems in which you have some lock-in of the momentum with some other degree of freedom. How about screening? Typically, as I just said, if you have a metal or a standard semiconductor, you say, I don't have to worry about the nature of the disorder, because even if I put a charge impurity, I'm going to have some very effective screening. And so what I'm going to end up is effectively, the very effective screening is going to make this charge impurity look like a very short-range scattering center. And so once I renormalize a little bit the disorder strain by the screening, some screening length, then I can just basically move on and use all the kind of machinery that I know for short-range disorder. For graphene, or system like graphene, in which you have linear bands, and so you have a vanishing density of states where the conduction and the valence band meet, the situation is different because basically the disorder is going to be renormalized, it's going to be smaller, but it's not going to change its algebraic. The fact that it's decaying algebraically rather than exponentially in real space, that doesn't change. And so you cannot avoid, if you have charge impurities, to have to treat them in a more sophisticated way, basically as a long-range scatterers. And that's a major complication for Dirac materials. I would have to say that even for a graphene, this is really true if you're close to the Dirac point. If you're away from the Dirac point, you can recover back the situation of a very good screening, and you can treat the disorder at short range. There is another complication if you're close to the Dirac point, and the complication is the following, is that now you can imagine that if you're at the Dirac point, the density of states is 0, you don't have any density of states, but now if you have an impurity, like you change the density of state from 0 to something finite. That's not really a negligible perturbation, okay? So that's a very major change and can be like positive or negative. And so as a consequence, you can imagine that in a real system in which you have some impurities, in reality, you're always going to have some like positive or negative density, so basically meaning like an abundance of electrons or a lack of electrons. And so you really have an average, you have 0 density, but locally you always something different from 0. And so as a consequence, in the real system, most of the times it's not really accurate to talk about Dirac point physics. What we really have is it's a charge neutrality point. Overall, your system is neutral, but locally you always have fluctuations. So the density fluctuation close to the Dirac point, because the density is 0 nominally at the Dirac point, any kind of fluctuations around that point is really the whole physics. It dominates the physics. If I go back to the situation that I mentioned at the beginning in which I do have a gap, if the gap is small compared to the amplitude of my fluctuations, then you can see that I'm going to have this interesting situation in which I have regions with a majority of electrons, then in red, and then I have a region that is in which I have a gap, and then maybe a region where I have holes. So I have this alternation of electron puddle, insulating region, hole puddle, and so on and so on. And the transport across this kind of situation, it's an interesting problem. We have an expert in the physics department here, Boris Shklovsky, that is, wrote a, kind of seminal book on this already 40 years ago. But the whole issue is rediscovered now because of this system in which you really have the situation in which this gap is comparable to the size of this disorder. Okay, so how do we, the first thing, if I want to calculate the transport property close to the Dirac point, the first thing I need to do is to somehow model the profile of my electrons on my graphene. And so the standard, the natural thing to do would be basically, okay, I know, the best system, one of the best and most efficient way to do that is using DFT, density functional theory. And so I can try to basically build a calculation based on DFT in which I take the graphene, I put my carbon atoms, and then I put some disorder. The problem with that is that if you want to model this long-range disorder, you have to use a very large primitive cell. And so the computation becomes very, very expensive. And so we thought about that, and so we basically then decided, okay, let's simplify a little bit the DFT approach. And so basically the way to do that is replacing the full operator for the kinetic energy also by function of the density. Okay? So if you know your bands, you can easily calculate what is the form for this functional of the kinetic energy, and then the rest is the same. So you have an arbitrary part, an exchange correlation part, if you want, depending how you want to be, how sophisticated you want to be. And then you have this term that basically couples, now completely lost. This is maybe, that's a little better. Yes. Oh, thank you, Eric.
This is just mine, but the top one.
The top, the one with the sun?
The one closest to the laser. Try that. Yeah.
Thank you.
Yeah. If it runs out, you have batteries.
I think I have some batteries also, but so yes, the key term here is this term that couples the disorder profile to the density of your electrons, and then you have a chemical potential term. So now, of course, I can do this basically replacing my full kinetic energy operator with the functional, as long as the profile of the density changes slowly. What I mean by slowly is basically changes on wavelength that are larger than the Fermi wavelength, the local Fermi wavelength. And so this is not always true, but it's true. For example, for graphene, we found out it is true as long as the impurity density is comparable. It's the order 10 to the 11 per centimeter square. But this is something that you have to be tested. Has to be tested system by system. But this is the general strategy. So once you know that this condition is satisfied, then you can use this approach, and this is a computation very cheap, and so you can simulate very large system, and you can calculate all the profiles that you want and do disorder average and so on. And so these are just to visualize. So this is, for example, for a single disorder realization. This is the result of our calculation, and so these are the results that were obtained using STM years ago by the group of Cromie in Berkeley. And this is one of the first papers that was published on this issue, just showing that you do have electron-hole parallels, but the resolution here is micron, so this is not really helpful to be quantitative. But here you can see that you really have these electron-hole parallels that are of the order like tens of nanometers in terms of, in size. So now, fine, you say we have this approach. We can see, we can basically know what is the profile for the density close to the Dirac point. How you do calculate the transport? Or before I go there, this is a recent experiment that, in collaboration with that we had done with Eva Andrei at Rutgers. And so what she has done basically is to have two layers of graphene, so one single layer of graphene, another layer of graphene. And the beauty of these van der Waals systems is that, as we also heard sometimes in the morning when you're growing, but if you exfoliate them, you can basically have a twist angle that basically makes them completely decoupled. And so what the advantage of that is that by being the two lattices are completely in a mismatch situation, and so typically you don't want that. You want somehow maybe have strong coupling. But on the other hand, let's say that you really want to probe the properties of the bottom layer or the top layer. So the complete mismatch basically allows you to completely do not modify the electronic properties of the system you're studying, but it still allows you to do some effective screening of the charge impurities that you might have in the system. Okay, so this is exactly what happens. So this is the profile that they obtained from STM for the single graphene layer. And now when you have two graphene, GG, then you can see that the amplitude of these density fluctuation is much reduced. At the same time, you don't lose the ability to gate the bottom graphene layer, and also in principle, if it's a different system, let's say you have molybdenum disulfide or something, because of the lattice mismatch, you do not modify the properties of your bottom system. So this is like a result of our simulation, but more interesting than that is to show also what happens if you do Landau spectroscopy. So this is the Landau spectroscopy for a single graphene layer. You can see that you can identify some of the Landau levels, but if you have the two graphene layers, then you see many more Landau peaks and much sharper. Okay, so that's another way to say that both the quasi-particle relaxation time and the scattering time are reduced by these additional graphene layers. So graphene basically it could be used as an effective screening system. So going back to the problem, now I want to calculate the transport properties of these. So the way to do this, one way to do this, is a semi-classical way. Is effective medium theory. So the idea is the following. I have my profile for the density. Then once I have the profile, as long as I have the size of the paddle is larger than the mean free path, and the resistance between paddles is smaller than the resistance that I get from scattering within the paddle, then I can use this effective medium theory. And so the way you proceed is basically you calculate the local value of the conductivity. So from the profile of the density, you know the density, so you can calculate the conductivity. Once you have that, you have a profile for the conductivity in space. And then you do an effective, you replace that by an effective medium that is homogeneous, but has a conductivity that is an effective conductivity. So the way in equations like this, you have a relation between J and the gradient of your potential. And then you average over position, so you should do this. But then you do this step is the critical step. Instead of the average J being the average of sigma times the gradient of V, you replace this by an effective conductivity, and you replace this by the average just of grade V. So it turns out that if these conditions are satisfied, you can do that. And the effective equation that you obtain is an implicit equation for this sigma effective. Given by this integral, where Pn is nothing but the probability distribution of your density, or if you wish, it could be like P of sigma if you don't know. So this works remarkably well, as simple as it is. So here I show some results for the case of the charge conductivity. So this is our result. So basically, we can recover the value of the minimum conductivity, and then the crossover, and then the linear scaling of the conductivity as a function of the gate voltage. These are the experiments that were obtained almost now 10 years ago by Andre Geim. But more interesting, we can also basically, this is a comparison between our result as a function of the impurity density for the minimum of conductivity with the conductivity, with the minimum conductivity was obtained by Michael Feurer by changing the amount of scattering centers. And so you can see that he also finds that basically there is the interesting behavior that this does not depend much on the amount of disorder that you have in the system, as we also find numerically. And so this is interesting. And it's, the reason why this happens is basically because of a competition, a compensation. So basically, as you increase the amount of charge impurities, what you're doing, you basically you reduce the scattering time, but at the same time, you create more like a stronger density fluctuation, so higher density of states. And so the two things just work out to be almost compensate each other completely. And now you can also understand why it was very tempting to identify this value of 4 as a universal value for the minimum of conductivity, even though it just basically it's not really universal. The universal value is down here, but typically is not reached in these large graphene samples. So we also apply the same technique to calculate thermoelectric effects. So in this case, you know, again from standard textbook, J is the current. Gradient of V is the gradient of the electrostatic potential. This is temperature. And so these are the linear coefficients. So this one is basically the conductivity. This one is the thermal conductivity. And these two are the Seebeck coefficient. Actually, yes, so these are the off-diagonal, and the Seebeck coefficient, we call it Q, the thermal power, is the ratio between L12 and L11, the conductivity. So if you do a calculation assuming that, this, for example, graphene is homogeneous, you find the Q scales like 1 over the square root of n. And so it's clear that when the density goes to 0 at the Dirac point, you know, these things seems to diverge. Would be great, but something has to give. And so what's happened there, basically you enter the electron hole paddle regime. Okay, so you can see that also in the experiment they see this bending over like that. And so, you know, it's slightly, the equation is slightly more complicated, but the idea is exactly the same. It's easy, you know, you can see that it's the same equation that we had for the conductivity for the diagonal coefficients, L11 and L22 is the same kind of equation. For the off-diagonal, it's a little bit more convoluted, but it's still the same idea. You replace the disordered system with an effective homogeneous system with this effective coefficient, L12. And then once you do that, you can basically calculate what is the thermal power as a function of density, and you see, sure enough, that basically this divergence is cut off by the electron hole paddles and bends over like this. And it was surprising to us that at least when the experiment that we had at that time, we also find some decent quantitative agreement. I think this was a Philip Kim experiment. Okay, so now just quick point about the case of bilayer graphene in which I put a gap. So I apply a perpendicular electric field, I create a gap. And so what I'm plotting here, as I told you, in that case, basically I have regions with electrons, region with holes, and a region that is insulating, regions that are insulating. And so you can imagine that if I open a gap, my Fermi energy is in the middle of the gap. If I don't have any disorder, the whole system is insulating. So in that case, basically, no disorder and find a gap. Basically, I have, you know, the fraction of the sample that is insulating is equal to 1. So I'm here. Then I start adding disorder, and so the disorder basically pushes the Fermi energy up and down, and so I started creating electron and hole puddles. And so the fraction of the sample that is metallic start growing a little bit. And so it's like, let's just, you know, and I'm keeping my Fermi energy fixed, so basically I'm keeping my average density 0. So I'm moving along this line. And so you can see that at one point, by doing anything else but just adding disorder, I cross a point where I have more than half of the sample, this is what this red line represents, that is metallic, okay, even though I did not change the gap. So this is like a little bit counterintuitive result that you have when the gap is small compared to the strength of the disorder, is that by increasing the disorder, you make the system to behave more like a metal than an insulator. So this is just to visualize a little bit what happens around this point. At that point, you can see here I have a lot of white, meaning that I have most of the sample is insulating, and here I have a lot of red and blue, meaning most of the sample is metallic. And so I can then basically use this as a crossover value that tells me that if you're above this value, you're going to have a metal below, you're going to have an insulator, and call that some sort of like a delta critical. You know, like a critical value of the Fermi energy above which the system is going to be metallic. And you can see that here what I'm plotting delta critical as a function of the impurity density. And you can see that as I increase, let's just follow, for example, the red line. This is for a given band gap of 125 millielectron volts. As I increase the disorder, the delta critical first, at zero disorder is exactly equal to the band gap. But then as I increase the disorder, this delta critical keeps going down. And then for a large enough disorder, it goes all the way to zero, meaning that at this point, basically, I just need a Fermi energy of the very small Fermi energy to push all the system to be more than half metallic. And so this was interesting because it explained some of the experiments that were done about 5 years ago, in which they knew from optical measurements that they had a band gap of 100, 150 millielectron volts, and yet when they were doing the transport measurements by estimating the relaxation over temperature, they were estimating that the gap was like a fraction of a millielectron volt. And so this large discrepancy was a little bit puzzling, and this is a possible, I think, quite easy explanation for that kind of situation. Okay, so, but so far, basically, I mostly gave results in the semi-classical regime, in the Boltzmann regime, and effective medium theory. But there is more to life than that, and that has to do with quantum properties. And so one typical example where you really see quantum mechanics in play is the so-called Klein paradox. So if you take a standard two-dimensional electron gas, like a semiconductor, and you put a barrier, most of the particles, most electrons are going to be bounced off the barrier, but there is a little bit of tunneling due to the quantum tunneling. But now, if your particles, if your electrons, instead of satisfying the Schrödinger equation, satisfy the Dirac's equation, something quite unusual happens. The electrons, if it comes in exactly perpendicular to the barrier, it goes through as if the barrier is not there. Okay, and so this, of course, it's a quantum mechanical property, and there is no hope to capture that using simply Boltzmann theory. So what do we do? One technique that I think maybe some people in the room are familiar to deal with the quantum mechanical transport is non-equilibrium Green functions. Okay, and so that's a very powerful technique. The problem with that technique for our purpose, it was that it's a computationally expensive, meaning that in the non-equilibrium Green function approach, your spatial resolution is basically atomic. Okay, but here, as I say, we also want to be able maybe to take into account the fact that you have long-range disorder, and so it becomes computationally too expensive to use that kind of approach, and so we use a transfer matrix method. So let me just explain for the case of graphene how this works. So you start from Hamiltonian, you add your disorder. Now this is the profile of the disorder, take into account the screening and all of that business that I mentioned before. At this point, basically, you write how the wave function basically the gradient of the wave function along the x direction, that is the direction along which you're trying to propagate your current, is related to the rest of the wave function. And so this allows you to define a transfer matrix M that basically relates the value of the wave function on the left of the sample to the value of the wave function to the right. Once you have this M that I give, this is the expression for the case of graphene, but it's not important for what I'm trying to say here, is that you can calculate then the transmission probability T, and then once you have T, you can calculate the conductance simply taking the trace of this transmission probability T. So why to use this method rather than non-equilibrium function? As I say, because I have the option to basically, if the profile is smooth, I can imagine that the slices that I need to take to divide my sample on the x direction, they don't have to be atomically sized small. So they can be like 1 nanometer or 2 nanometers. And so in that case, I can save a lot of computation. I can do much bigger systems. The problem with this technique is that it needs a lot of babysitting, meaning that you really need to basically do some tests to basically realize what is the right thickness for your slices to basically give you reliable results. But once you're there, it can be very effective. And so we apply for the first time to calculate, for example, what is the transmission probability across a PN junction. So in the experiments, what they do, they place a top gate. So the top gate creates a bump into the graphene potential profile. But then we know you also have some charge impurities, so you can see how this basically is not really smooth. And the question we had is that can you still see quantum tunneling even if you have some sort of perturbation of this nice bump? And the result is that yes, so let me show you here. So this is the result for the clean case. So what I'm plotting here is the amplitude of the resistance as a function of the top gate. And let's fix the back gate. And so I'm just changing the top gate. So what I mean by that, I'm changing the height of the bump that the graphene electron sees. And I can see I have this oscillation. The resistance goes up and then comes down again. Why does it come down? Because of the Klein tunneling, okay? And so on. So then I cut here, and then I can see the black line is the result in the absence of any disorder. And so I have this oscillation that is signature of this Klein tunneling. If I put some disorder, I can see that these oscillations, I can still see them, okay? So there is a critical value of the disorder after which they disappear, but you can see that I can push the disorder quite a bit and still identify these oscillations. So despite the presence of disorder, I still have signature of this Klein tunneling. And so what is the simple criteria to see this Klein tunneling? Basically, the simple criteria is that as long as the mean free path in your graphene sample is smaller than the length, than the width of the bump created by the top gate, you're going to be able to see these oscillations, and so you're going to be able to see this Klein tunneling. And these are experiments that were done by Exeter group, in which they exactly see the same these. So basically, you can see here, you can see these oscillations. And this was for a different sample in which they don't see these oscillations. And the reason is because basically they had a different mean free path. Okay, so another thing that you can calculate once you have a way to calculate quantum transport are the so-called universal conductance fluctuations. So this was discovered like in the late 80s and 90s. This is a very interesting effect. So basically, if you have a system and you have disorder and you measure the conductance, you get a value. Then you do the measurement like half an hour later, you get a slightly different value. You keep doing that, you basically get many different values. But the spread of this value, it turns out to be a universal value. Okay, so this is a universal conductor fluctuations. And here is an example, for example, many different measurements as a function of a small magnetic field, and you have different traces, but the width of this black area, it's a universal value. And so what we wanted to find out is that, well, this was all shown theoretically for the case of short-range disorder, but now we have long-range disorder, for example, in graphene. The fact that you have long-range disorder, does it change this result? Yes and no. So here I show the dashed line basically represent the universal value that you would expect. And then here I have different results that we calculated using the transfer matrix approach, increasing the amount of disorder. So you can see that I have a small disorder. I have the conductance fluctuations are larger and also have some interesting oscillation that basically mostly due some boundary condition that I have. But then if I increase the disorder, this oscillation quickly disappear, but still the value is not the same as universal value. And then, I have to push the disorder quite a bit to get to the universal value. So the bottom line is that in system like graphene, because of this presence of these puddles, there is a much larger range of value of impurities for which you're going to see non-universal value of this universal conductance. And another interesting consequence of this behavior, you see, is that, as I mentioned in one of my first slides, is that in a two-dimensional system, the change of the position of one impurity can change the conductance by a significant amount, E squared over H. So now you can imagine the following situation. So like let me say, maybe before going to this, let me just say the motivation for this is that people had measured the 1 over F noise in graphene samples, and they see the strange monotonic behavior. So this is close to the Dirac point, then it goes up, the 1 over F noise, and then it goes down again. And so 1 over F noise it's a tricky business, but a possible mechanism by which you get the 1 over F noise in a system like graphene is that you have a single impurity moving around, hopping, and the hopping has some time scale t. And so by that, you're going to change the value of the conductivity. So as a function of time, because your impurity is moving around, the value of the conductance change. This would not happen in 3D, but it does happen in 2D. And so by just calculating, and so then as a consequence, the spectrum of your noise is going to be proportional to the amplitude of the conductance fluctuations divided by the average value of the conductance. So you can see that by calculating the conductance fluctuations, we also get a handle of the strength of the 1/f noise. And so by just taking this type of result and dividing by the average value of the conductance, we're able to plot the 1/f noise as a function of the density, and we also recovered this non-monotonic behavior that basically we attribute to this non-universal behavior of graphene when the impurity density are not too high. So how much time I have? About 5 more minutes. Okay. So this is a very quick slide about the quantum Hall effect. Hopefully you've seen this before. If you haven't, you're not going to learn it from this slide. But what I want to make contact with what I said before is that it's, we now know from, in 82, Towles wrote this very seminal paper in which he basically pointed out that this, the whole conductivity, so basically the value of the conductivity that is, so you apply a perpendicular magnetic field to the 2-DAG, and then you basically have a voltage drop along the xy direction that is perpendicular to the direction at which you apply the electric field. So this is sigma xy, is the whole conductivity, and it can be expressed if you just use Kubo formula. So basically use the same procedure that I mentioned in my second slide, linear response theory. Then you plug back you calculate the current correlator, and then you can see, you can show that basically the whole conductivity can be given by this expression where um are the eigenstates of your system in band m and momentum k. So this is the gradient of the eigenstate u in band m with respect to k. So this is, I should say, gradient with respect to k. Now, it's interesting to see that basically this expression for the whole conductivity can basically be interpreted as the integral of a vector of a Berry connection, and basically that is going to give you a Berry phase that is given by this expression. So this is a property of the occupied bands, and this is a topological property. What I mean by that is that if you have an insulating system with a gap, and so you occupy all the band up to the valence band, this number is not going to change no matter what you do to the bands of your system unless you close the gap. Okay, so in that sense, it's a topological property. And so typically this number is either 0 or 2 pi, but it turns out that in the quantum Hall regime, this number is going to be 1. And so this is the so-called Chern number. You sum over all the occupied bands, you get a number. So as I say, typically it's a multiple is 0 or 2 pi, but for in the quantum Hall regime can be any kind of like 1, 2, 3, and so on. And so now what happens is that, for example, if you have a normal insulator, you have n equals 0, and then here you have n equal 1 in the quantum Hall state. So as I say, this number cannot change unless you close the gap. So then in order to go from 1 to 0, something has to happen at the boundary. What happens is that you close the gap. So what it means is that you have an edge state. Okay? And so this is the origin of these edge states, at least in this kind of picture. You can then go from the quantum Hall effect to the so-called topological insulators. It's the same idea, but now your topological invariant is not just the total Chern number, but it's the difference between the Chern number for the spin up and the spin number and the Chern number for the spin down. And this number doesn't have to be 0, and so it can be different from 0 or multiple of 2. And in that case, you have a non-trivial insulator, as we call topological insulator. And so this is the experiment in which basically they put this well. And they saw that basically there is this quantization of the spin Hall current. So this is the 3D. So again, this is probably way too much to explain in the remaining few minutes. But the idea is that you can basically follow a similar procedure, just more complex, for three-dimensional material and identify which materials have this kind of topological invariant that are different from the standard values of 0 for trivial insulators. The last thing I want to mention is that, okay, now we have these new materials of topological insulators of graphene, and so one thing we wanted to look into is that what if you combine them? It turns out that the surface of a topological insulator is almost an exact ratio 1 to 3 with the unit cell of graphene. So for antimonium telluride, for example, it's less than 1% the mismatch. And so you can expect that there might be a good coupling between the Ti and the graphene. And so what is the interest of that? We know that the TIs have a very strong spin-orbit coupling, and so our thinking was that can we induce a strong spin-orbit coupling into the graphene layer and get a high mobility two-dimensional system with a strong spin-orbit coupling. We know that the TI surfaces typically are pretty dirty, so low mobilities. And so we did the calculation. Turns out you can. We also find out that actually these, so the blue and the red bands are the Rashba-like bands induced into the graphene by the proximity of the topological insulator. And what we found is that these bands, this splitting, this Rashba splitting, is much larger for the case of bilayer graphene compared to the single layer graphene. So the message of this slide is that if you want to try these, you're probably going to have a bigger effect if you put bilayer graphene than single layer. We had this theory. We thought it was nice, but maybe it's difficult to do. But now people have done this. So these are samples by the MIT group. Hadar now is in Israel in Raqqa Institute, but he basically was able to make these samples and see some tunneling measurement. And then more recently, the group of Ahsan basically was also being able to do ARPES on these kind of systems and see something that suggests that there is some coupling, even though in this case it looks like there is a big mismatch angle between the TI substrate and the graphene layer. So why to look into these things? Well, once you have this kind of system, our idea is that now I have a high mobility two-dimensional system with a strong spin-orbit coupling. I can try to drive a current through this two-dimensional system and induce some interesting spin-based effect. In particular, for example, induce some spin accumulation at the interface between the graphene layer and a ferromagnet, and induce dynamics in the magnetization of the ferromagnet on top of the graphene, inspired by experiment by the group of Dan Ralph in Cornell, in which they do this for the TI plus permalloy. And so we said, well, if you put graphene, it should be better. And so we did the calculation. As a matter of fact, the strength of the FET, it seems to, I put the same plot twice, so you don't forget. But the message here is that not only you get a much stronger FET, but also you get a much stronger FET for much less dissipation into the layer for current dissipation because the high mobility of graphene. And so actually this was the last thing I wanted to say. So just an overview of what I said. 2D is different. So like paraphrasing, like less is more. Important difference between the 2D systems. So of course also you have to be careful if it's talking about graphene or standard 2DEG, and there are very interesting differences. For Dirac system, I hope I took home the message that if you have charge impurities, then you really have to be careful about treating them as long-range disorder. You cannot treat them as short-range disorder because of the poor screening of graphene close to the Dirac point or TI surfaces. The chirality is also important. In general, you cannot neglect it, and you have to keep track of it if you estimate the transport time. You have unusual quantum transport effects as Klein tunneling. And then all of these, basically, it's related quite tightly to these quantum Hall effects that are very interesting. Thank you so much for your attention. When can you use it? You can, well, basically, you can always use it, but when is it convenient to you to use it? Basically, when you get to the point in which the disturbances in your system are close to the lattice size, then I don't think you gain much. You don't gain anything by using that approach rather than standard non-equilibrium green functions. That is also maybe easy to implement, and kind of like you don't have to worry about testing that your program basically converges and everything. So in that sense, you can always use it. It doesn't pay back to use it when the impurities are short range or when you have like structures within your sample that are close to the lattice size. Yeah.
So one question, connection to the question that we asked.
Yes.
So when one uses the Dirac equation, one has this fermion-Darwin problem.
That's right. That's exactly that's another good point. So, for example, if you if you want to study the situation in which you want to neglect the intervalley scattering, then if you do a lattice model, you cannot avoid that. And so, but if you do basically, if you use this transfer matrix approach, you can discretize a continuum model with only one valley, and you can ask questions about exactly what happens in the limit in which you don't have the other valley. And so, for example, that was very important to be able to calculate, for example, the anti-localization of graphene systems compared to,
So, yeah, let's thank the speaker.
Thank you.